they'll be demonstrating on crop type mapping, something that for the people who are attending most of our meetings, they know how important this is, especially to BACO, because these are some of the areas that we like to collaborate on going forward. So we give them a small assignment on how to integrate some of the works that we've been doing into the DEA platform in order to map crop type within certain areas in Kenya. So this is what they'll be presenting, and they had moved everything to the sandbox. My sandbox is still opening, and they'll be using this particular computer to do their presentation. So as they start the talk, we're also waiting for the servers to start, but they'll continue with some of the things that they'll be demonstrating later. So to you, Emmanuel and Cornel, all the best.
Thank you, sir. Good afternoon, everyone. Hello. Good afternoon. Okay, thank you. I'm Emmanuel Kiptich, a student from the Dan Kimathi University of Technology, and I've been here for the past 2 months here at RCMRD, where I was introduced to the Digital Art Africa platform, and within that span of 2 months, we've managed to learn, and we've been running a number of projects within the DEA platform. And today, I'm glad for the chance of being offered. We present one of the projects, that is the crop type mapping using the DEA platform. And we, as the sandbox is loading, I would like to mention some of the things we are going to go through today. This exercise was an assignment, but the kind of outputs we presented have been of high presentable. And on last week, Friday, we presented to the RCMRD team. And today, I'm glad we are presenting here today to the Digital Art Africa entire team. Thank you. I see it's ready, and let me share my screen. Hello, can you see my screen?
Yes.
Okay, thank you. So this model, we have incorporated the random forest classifier to spectrally differentiate between different types of crops, and our area of study was Trans Nzoia. That was where we could easily find the field labels regarding the different types of features, and particularly the different types of crops in that region of Trans Nzoia County. Within the DEA platform, we managed to incorporate the random forest, where we process the data and we train the model, and we applied the model to our area of study after analyzing the accuracy of our model. I would like to welcome my colleague, Mr. Cornel, to take us through the data preparation, and then I will handle the model building and the application of the model. Thank you.
Good evening, everyone.
You're welcome.
Good evening. I hope I am audible enough.
Yes, I'm hearing you.
Okay. I am Cornel Cheptumo, a final year student from Jomo Kenyatta University, and currently a GIS intern for RCMRD. So we were given a little assignment concerning crop type mapping, and we are glad to present our findings today. So I will take you through the first half of the presentation, which incorporates loading the training data all the way up to training the model. So if we can begin, the first step in our findings, we set up a Dask cluster. This Dask cluster enables parallel computing, which will enable us to make use of our storage from the sandbox. Our next step is we will load, if you can see the screen well, we will load our training data sets. The training data set that we used for this particular project was an already digitized data obtained from Severe East Africa. So we'll quickly load the training data into a sandbox. First, we will begin by importing our GeoPandas package, which will enable us to read our spatial data. And we will call this training data set, training data. And then we will read the training data and call it vector old. And then we will read the first 20 lines. And here they are in our output. Then the next step, we will load the data. We will load the training data in relation to the image. And if you can run this code, it will show exactly where the training data are. Let me load it. Let me load the whole thing. If you load this code, it will show our polygons, our training data polygons from Severe in relation to in relation to the actual image. So we can see our area here between Trans Nzoia, with Kitale being somewhere around here at the center, with Mount Elgon on the far side and another forest on the other side. The next step, you're going to connect to the data cube, and we're going to name it model development. Then we will go and set up our image parameters. We have our latitude and longitude data over here. We'll set up a buffer of 0.3 on the latitude, 0.5 on the longitude, then add the buffer and the latitude and longitude parameters. And then after running the code, we'll display our area of study. If you can see well, here's our area, and it's a Trans Nzoia area around Kitale. Then we will quickly go to the next step, that is loading the Sentinel data that correspond to the training data that we collected. So we want to load our own image here that will correspond to the training data that we obtained from the Severe dataset. So we load our query here, which will contain the resolution, which is a Sentinel image of negative, which will contain 10-meter resolution. And we have our measurement bands here from blue to shortwave infrared 2. And we will create another query here that will load our data. We have our Sentinel-2 products, our combination of the buffer and our image parameters. The time which we obtain our image is 2019, around May 2019. So we are going to set up our CRS, which is 6933, and we're going to group by solar day. Then we're going to display our image. We'll run the RGB, and here is our displayed image. Hope we are okay up to there. We will export this downloaded image of ours, and we will export it and save it for later use. So we're going to import the RightCog package.
Yes, David, I think we lost the connection.
Sure. Yes. Hope we are back. We are back. Hope I am clearly audible.
Yes, please.
Yes.
Yeah. Oh, if we can retrace our steps from the displaying our polygons, if that's okay. So we have already displayed our polygons and displayed our polygons on an image. We connect to the data cube. Then we load our Sentinel data, and here are the image parameters and the buffer. Then we have displayed our image here, which is an area, a Trans Nzoia area around Kitale. Then we have loaded our Sentinel data, and here is our parameters with the resolution and the bands. We are going then to display our image, which is displayed here. This is our 2019 May Trans Nzoia image. Then we are going to save this image that we have loaded. We're going to import the RightCog package, which will enable us to save our image, and we will name it rasterfile TIFF. Then we will go to the next step. We are going to model the training. So the first step before we model the training, we are going to match the projections. We're going to check the projection of our training data. And if you run this code, it will bring and display the CRS of the image of the training data, which is 4326. And the CRS of our image here at the top is 6933. So you want to align the CRS of both the training data and the image. So we are going to convert the training data from the CRS to match the one on our image. So if you run this script, it will convert our CRS from 4326 to 6933. Then the next step, we are going to identify our unique values in the training data, which we're going to use in our class name. So we're going to import the NumPy package, which will help us in mathematical manipulation of our data. And then we are going to read the classes from our training data from the attribute name. So here the arrays of the training classes are displayed. They are about 9 from build to water body. Then we are going to create a dictionary to convert class names into integers. Then we are going to call that dictionary class dictionary. Here is the dictionary with the key values and the classes. Now, next we're going to extract raster values within each shapefile. We're going to run through each shapefile and extract their spectral signature within the boundary of the shapefile polygons from our training data. So we're going to import the following packages, which are raster stats, and this will help us read our raster images and rasterize our data. So this we are going to call our raster file, which is our image that we loaded from the sandbox, and we named it raster image. So we're going to we named it raster file. So we're going to call it again raster file, and we're going to define all values. This is a custom function for getting each value from the raster file. So we're going to get each value from our file. Then we're going to name the parameters of the data within our training polygons. So we had the attributes name and the attributes geometry. We're going to rename it label for the name and geom for the geometry. Now we are going to read the raster data matching the geometry bounds. So we're going to read the spectral signatures that are in between the boundaries of our shapefile from the training data. So we are going to read them in the following code and save them as our window, and save it as a window. Then we are going to store our window information and call it window affine. Then the stored window information, we are going to read the stored image. We are going to read our stored image information and call it FSRC, so that we don't confuse it with our image here, which we called it SRC. Then we are going to rasterize the geometry. We are going to employ our mask capabilities here, and we are going to rasterize our image. Then we are going to fix. We are going to for each pixel where our query here is true, we will name it. We'll add a pixel. We'll add the pixel data to X, and if it's also true here, we'll add the labels to Y. Then we are going to convert the training data lists into appropriate NumPy array shape and format for skitlan. So we have the pixels for training and the X pixels for training, which we added here, and our Y pixels for training, which we are going to convert into a NumPy array shape and format. And if you run this code, here is our format, which will be acceptable by our model. Then next, we are going to explore the spectral signatures of our data. And if you can, we import our matchlib function here, which will enable us to display our image and graph. So this image is a band. This diagram over here is a band intensity full overview diagram. It gives us the reflectance value of our band, of our reflectance value in relation to our bands. If you can see here the blue band representing the built-up area, you can see its reflectance value in relation to our bands. Then we are going to enhance classification with remote sensing indices. So the two indices we're going to use here is NDVI and NDWI. NDVI is great for photosynthesizing plants and NDWI for water. So we're going to display our formula here, which is the A minus B over A plus B. So we are going to define our bands here for the indices. That will be for the NDVI, it will be the near infrared minus the red, and we have the following here. So we are going to apply our bands here to this formula, and it will calculate our band indices here. Then we will concatenate the results, which will combine and merge the results, and we'll have our resultant 2D array over here. Then the next step, you're going to train our random forests. The first step in training the random forest, we're going to split our data into two. We will have our training data sets and our testing data sets. The training data set, we are going to use it to train our model, and we will use 20% of the data set to test our model, to see and to test the model to see if the model is accurate and can be used or not. So this is the script for testing our model, and we will apply a random state here. A random state enables the code to repeat itself. Then we will go to the next step, which is weighting. If you can see our training data here, our training data is biased, so we have to apply a form of weighting mechanisms to reduce the biasness of our data. So we will load them, and we will load the classes, which we call them the class weight dictionary, and we will weight them, and we will get our final output, which is the weighted data of the 10 classes we had. And that's all. Thank you. And my colleague Emmanuel will take over from the next procedures. Thank you.
Hello, once again. Any question up there? Hello? Okay, basically what he just...
I wanted to, if you could scroll back to the place where you used Dask at the beginning.
Okay.
I wanted, I just want to check if there was a compute. Yeah. Oh, okay. I was wondering if you use Dask, why when you scroll down and you load the data, it should show chunks. If you scroll down to where you loaded the the Sentinel data.
Okay, it cannot show here directly, but it is being used in the random forest classifier.
Oh, okay. You weren't using it when you were loading the data set.
Yes, but it is being used in the random forest classifier.
Okay, thank you.
Okay,
I have one question too.
Yes.
So thank you so much for this presentation. I think, as David said, we are so interested in it because we have the crop typing as a proposal. So thank you so much for sharing this model with us. My question is related to the training data.
Yes.
Because in our proposal, we have to go to the field to collect data. And in our presentation, already I already saw the training data that you used. And my question is, what will be the difference between this training data and the data that you have to collect? Because in your proposal, I saw that you have to go to the field and collect data. So what is the difference between the training data that you are already using and the one you want to collect from the field? Thank you.
What we mean here by training the data is that adding the spectral information to each and every polygon collected in the field. And the polygons here we are using, they are back to the date 2019. That's why even the image we have loaded here, it reads 2019. Have I answered your question?
No, so my question is, how you collect this data? Is it from the field or through the high-res images?
No, the field data, and they were collected back in the year 2019 by the surveyor and RCMRD.
Okay.
Yes.
Thank you.
Okay, I have a question also.
Yes.
Okay, my question is also about training data and test data. And if I follow very well the presentation, you select 20% of the data for validation data.
Yes.
And 18 for training. And you say that is polygon. And you know that the polygon have different dimension.
Yes.
How you select this 20% from this one? Because it's not, yeah, that is my question.
From the entire training data, the method of selecting of splitting into the test and the trail, they were randomly picked.
Randomly picked, okay, thank you.
Yeah, yes.
And why the 20% for test data?
20% is a value that has been agreed on. Yes.
Thank you. Okay, thank you.
Okay, after now rasterizing the polygons with the spectral information of each and every class, this spectral graph helps us to understand that each and every feature are separable for us to continue with the model.
Yes,
and you can see for each and every class here, it is clearly separable, except only around this wavelength where there is such closeness. It's because the crops are much related between this band. Okay. The next step will be now building the model, and we've utilized the random forest classifier to classify our image. And the most important, you can see in each and every cell, we've been importing a package in a place where we need it, and subsequently remembering it so that we don't import it for a couple number of times. So here we've utilized 200 trees, and these other parameters, including the verbose. Verbose implies the number of wording that will be shown as the model is running, for example, here and here, as well as when they will be predicting on the entire image. This kind of information here is controlled by the verbose value you define here during the initialization of the random set. This n jobs makes use of the processors, and by this -1, it implies that the random forest classifier is allowed to use all the available processors. And right from when we were loading the task, you must have noticed that we are utilizing the entire 4 processors of our DA server. After initializing the random forest classifier, it's good for us to fit. That fitting implies that we are now fitting our input into the target classes. And here, X and Y, X being an array is the training input, and the Y is the target value of each class Okay, that is it, and the output is this one. This maximum depth being 6 implies the number of bands that were loaded from the initial when we were loading the satellite data. You can see it from here. There was 6, all this one, and that is then what each and every feature is going to be based on during the classification in the random forest classifier. After that, it's good for us to assess the accuracy of the model, and through that we did manage to predict on the X test that those are the training data which was splitted. So from the built model, we are now predicting on the X test, and we are here plotting the confusion matrix of the same. And you can see of all the sunflower that were predicted, it is true that in the scale of 0 to 1, all of the sunflowers were predicted to be sunflower, except only for this class between the shadow, because our initial data had a class of shadow. You can see the values has been spread on, but we have a high accuracy when it comes to water body and also the built up class. Having that ready, it's also good to plot the tree interpreter, in that the tree interpreter shows what bands contributed to which class the most. And initially I had mentioned that the bands were 6, but here you can see that the bands are 9. It's because we had added some other helper functions, including NDVI, NDWI, and NDBI respectively in that order. And it is true, this 0 to these are the classes, and you can see that for each and every class here. For example, this 0 was a built up, and you can see the NDBI is the one that contributed the most. That is how to read that table. And having that, here is now where we are applying the entire model to predict the entire image. But back here, we can optionally save the model if you would like to apply the model in another area. Here, when now we are using the model, the most important command is this one to predict. Here, this one is the command to predict, and then this one is the image which we are now predicting. This one is the random forest classifier which we had initialized, and it is now the ready model. So you can see that the image which we are training is the one which the no data values have been removed, and this image is the same image in which the necessary indices have been added, and this image is the one we've just imported from the exported image initially. And should we run this cell, it's gonna take about 4 minutes, and these are the entire how the background information about our model, showing the number of trees, the current task that way, and this wording can be controlled by reducing the number of variables, and it will group the spectral pixels into the different classes as per the training data. That is it. And we can see here now our model has predicted the image. This one is the initial image, and this one is the new classified image. We can see that it did classify the clouds here. At least we have all these clouds. And then should we see here, it implies the different crop types. I will share a classified image, a symbolized image in QGIS. Yes, and this one is the forest. You can see it's very clear that way. Yes. Additionally, we can do some statistics, including the plotting of areas. These are the area plots of the Trans-Nzoia classified image. in squared kilometers, and you can see the forest being higher, and the planted farmland, that is the maize, water body, sugarcane, and the fallow land. All these are the classes that were there in our training sites. Thank you. That's my presentation.
Thank you very much, Emmanuel and Colonel. Yes, some questions from Bako in the chat. Yes, Bako, please.
The question by Bako about those starting with the pilot areas without any data already collected, I think the best approach is to collect the field data first of all. Then you come and input into our model. Yeah, we're going to share the script, but we're going to use a means where each and every of us is going to have a copy of it. Thank you. And just to mention, when you've imported your data, the field samples, it's good for you to have that in the attribute table, you specify this class name in which each and every polygon is going to be grouped. Yes, that is it. Thank you.
Thank you, Emmanuel. Thank you, Colonel, and thank you, the guidance of the supervisor, David Ongo, and the team. Thank you so much. Any other questions can be directed to David?
Yeah, I have one question.
Yes, please.
Okay, thank you, Ken. Thank you for this nice presentation. And we will talk about this data, but I don't see the accuracy result. Perhaps it's my internet, but you show already the result.
It's there, it's on display now.
Okay. Thank you.
Thank you so much. This sounded like a PhD defense. So congratulations, Emmanuel and Colonel, for this great presentation. Any other additions from the team? Victor, David Ongo, any other additions? Are you able to do more stuff for other countries, or for Tanzania it works very well?
For this particular one as a test, because we had labeled information from the field, we are hoping if we can have well, if Bako gives us very good data from where he is, that is labeled data from any country, we can try to replicate the same script and see the performance. Other than that, we are hoping also to test it for Zambia, the same script. We'll also do a test for Zambia, and we see how it performs. But so far, so good. We are hoping also, before these two gentlemen leave us, we'll have another presentation soon.
Thank you so much, David, for your guidance.